Hello and welcome to the week 4 review. The main two things that we covered in this week were linearization, and also we talked about reachability. But since we're going to talk about this more on Tuesday, I'm going to postpone this and just focus on linearization. So the idea for linearization is the following. If we have a linear system, we understand stability. But what about nonlinear? The most important thing is to understand stability near an equilibrium point. So the idea is that we can, if xe is an equilibrium point, which recall means that f of xe is equal to 0, because that means that x dot is equal to 0, we can linearize f using simple first-order Taylor expansion about the point xe, the equilibrium point. So I think I'm just going to do 2 more examples. We'll do 3 examples in class, but hopefully this will help. But the sort of general paradigm is the following. Let's let xe be an equilibrium point. And again, for simplicity, let's just assume that this is 0. Then, this tells us that near xe, Taylor expansion says that f of x, or in other words, near xe equals 0, f of x is approximately equal to f of 0 plus f prime evaluated at x equals 0 times x. This is now in the scalar case. And what happens in the vector case? So for the vector case, we have f of x is approximately equal to f of 0, now x and 0 are vectors, plus, not derivatives, but the vector of partial derivatives, so df dx1 all the way down to df dxn transpose times the vector x. So let's see this in action. Example 1. Suppose we have x dot is equal to alpha sine x times cosine x plus 1 over x minus 1 squared. Okay, so in this case, this is the very much nonlinear function, f of x. And questions I might ask is, show that x equals 0 is an equilibrium point. And then B, for what values of alpha is this a stable equilibrium point? So this is very similar to the questions that we, to the examples that we worked on in class. Well, how do we do it? So for part A, we see that if I plug in 0, I get that f of 0 is equal to alpha times sine 0 times cosine 0 plus plus 1. Whoops, that's obviously not what I wanted. Let's add a minus 1 there. Plus 1 minus 1, which is going to be 0 plus 1 minus 1, which indeed equals 0. Aha. So it is an equilibrium point. So now let's linearize. This is scalar, so to linearize I have f of x is approximately equal to f of 0, which we just saw as 0, plus f prime evaluated at x equals 0 times x. So I need to find what the derivative is and evaluate that at 0. So just taking the derivative with respect to x, let me make that even more clear. This is not x dot. This is the derivative of f with respect to x. So d dx of f is equal to alpha times times cosine squared x minus sine squared x plus minus 2 times 1 over x minus 1 cubed. And if I evaluate this at 0, f prime evaluated at x equals 0, I get alpha times 1 minus 0 minus minus 2. So this is equal to alpha minus 2 is the derivative. And therefore, the approximate dynamics, the linearized dynamics, near the equilibrium point are x dot is equal to alpha minus 2 times x. Now what do we know? In order to make this stable, this needs to be, the real part of this has to be less than or equal to 0. So the condition on alpha, if alpha is real, is that alpha minus 2 has to be less than 0, or equivalently, that alpha has to be less than 2. So let's do a more complicated example. A vector valued example. So let's suppose that I have x1 dot is equal to negative x1 times cosine x2 plus alpha x2 times cosine x1 minus 3 x1 x2, and x2 dot is equal to x1 plus sine x1 times sine x2. Again, another very nonlinear function. And similar, same two questions. Let's show that 0, 0 is an equilibrium point. But that's easy because if we just plug in, then we see that it's equal to 0. So checking that 0, 0 is an equilibrium point is easy because I get, let's call this f1 and let's call this f2. f1 of 0, 0 is equal to minus 0 plus alpha times 0 minus 3 times 0, which is 0, and similarly f2 of 0, 0 is also equal to 0. So now let's check values of let's linearize this. So to linearize, I need to use the vector form. So f1 of x for small x, this is equal to f1 of 0, 0, which we already know is equal to 0, plus the gradient, which is df1 dx1 df1 dx2 evaluated at 0, 0 times the vector x1 x2. Okay, and then we have to do the same for f2. So if we do this, so taking the derivative, so df1 dx1, this is equal to minus cosine x2 plus alpha times x2 times the derivative of cosine, which is minus sine x1, minus 3 times x2. And if I evaluate it at 0, this is df1 dx1 evaluated at 0, 0 is equal to minus 1 looks like just minus 1. Maybe that's not what I wanted because the cosine goes away completely, but let's keep going. Yeah, okay, so the alpha goes away completely, but so there's no alpha in df1, dx1. So what about df1, dx2? So this is now equal to positive x1 times sine x2 plus alpha times cosine x1 minus 3x1. And when I evaluate it at 0, df1 dx2 evaluated at 0, 0 is equal to 0 plus, there's my alpha, alpha minus 0. So it's just alpha. Now I have to do the same thing for df2. So let's remind ourselves what f2 is. f2 of x1, x2 is equal to x1 plus sine x1 sine x2. And therefore, df2 dx1 is equal to 1 plus cosine x1 sine x2. And if I evaluate that at 0, 0, it is just equal to 1. And, whoops, sorry about that. And df2 dx1, oops, df2 dx2 is equal to 0 plus sine of x1 times cosine of x2. Note that we don't need to do any product rule here because only one term is a function of x2. And if I evaluated this at 0, df2 dx2 evaluated at 0, 0 is equal to 0 plus 0. So that means, putting this all together, I have that x1 dot is approximately equal to f1 of 0, which is 0, plus the gradient. So the gradient is going to be the terms df1, dx1 evaluated at 0, and df1, dx2 evaluated at 0. So the gradient is going to give me minus 1 alpha transpose times x1, x2, which is equal to minus x1 plus alpha x2. And what's x2 dot? This is approximately equal to, I'm looking for df2 dx1 and df2 dx2. So this is approximately equal to the gradient 1, 0, transpose x1, x2, which is just equal to x1 plus 0, x2. And you can see from here that we have our familiar x dot is equal to ax. We've got x1, x2 dot is equal to minus 1 alpha 1, 0 times x1, x2. So now we need to know rules for stability. When is this stable? For what values of alpha is this stable? Well, all we have to do here is apply our usual rules, where there's nothing nonlinear about this. So for stability of linear systems, step 1 is always to compute the eigenvalues. So let's do that. We've got the determinant of that matrix, minus 1 alpha 1, 0, minus lambda times the identity. which is equal to the determinant of -1 minus lambda. Alpha 1 lambda, and this is now equal to minus lambda squared minus alpha. And what are the roots of this? So to find the roots, we can also flip the sign. So if I flip the sign, this is like writing lambda squared plus lambda plus alpha. Right? The roots of this polynomial and the negative of that are, of course, going to be the same. So that gives us lambda is equal to, I'm using the quadratic formula, negative b plus or minus the square root of b squared minus 4ac divided by 2a. This is the quadratic formula. So what do we need for stability? We need both roots to be negative, because everything is real here. So we need the real part to be negative, but everything is real, so we need them to be negative. So in other words, we already have a -1, and then we have plus or minus, so we need this term to be less than 1. So we need the square root of 1 minus 4 alpha to be less than 1, which is the same as asking that 1 minus 4 alpha is less than 1, which is the same as asking that alpha has to be greater than 0. So for all values of alpha greater than 0, this is stable. And those two examples show how we can use linearization to answer questions about stability, but only local stability for nonlinear systems.